Okay, why don't we get started? So as I said, I'm going to immediately dive into this nucleon structure topics. That's what we are here for this lecture. And by the time I get to the EIC, as I said, it's going to get more like a seminar, and hopefully the discussion time can be used to answer questions. So again, I show you this plot again, and now I'm going to talk about these experiments here, the ones in blue and green here. So strange quark form factors, neutron radius, and then not in this plot is the EIC potential. Okay, strange quarks. So again, I'll give you a historical context for why these experiments got motivated in the 90s. So by the 80s, it was clear there were C quarks in the proton. So here are cartoons that were drawn 1980s, and then 1990s, 2000s. Bear quark surrounded by the C. Jefferson lab started to measure the form factors. So you have the electric and magnetic form factors for the nucleon. Possible models to explain the electric charge form factor of the neutron were being explored by then. But then there was also the spin crisis, that polarized lepton scattering of polarized protons showed that only 25% of the proton spin is being carried by valence quarks. This is a well-known EMC effect. So the question was, are the C quarks playing a role? And in particular, can the strange quarks be playing a role in modifying the properties of the proton? And so for example, do you have, just like you have a pion cloud, can you have a kaon cloud? And how do you measure that? You measure the strange charge distribution or the magnetization distribution. And how do you get that? You have to measure a new form factor combination of of the quarks in the nucleon. And so the idea that was proposed in the late 80s was that since you can use charge symmetry to get at the U and D quark distributions by doing elastic scattering of the proton and neutron, so you measure both GEP and GEN, but you can also then do the strange form factor, and that gives you a new linear combination if you have 3 flavors that are active. And so this would be a new linear combination. And so if you already know what the proton and the neutron form factors were, you can get at the strange form factors, which would give you the strange distributions inside the proton to see if they are non-zero. Okay, so that's where parity-violating electron scattering comes from, because if you want this combination, you got to do parity violation. So here is more an expanded view. So again, you have the G Fermi Q squared over alpha, and then you have the electric, the magnetic, and the axial combination. They're listed here in terms of the form factor language. And then you can also scatter off helium-4, and then there is no magnetic contribution, and you just have the charge contribution. So that's very nice to be able to do forward angle low Q squared, which just gets the electric strange form factor. And then you can do backward angle scattering to enhance the GA component. I won't talk much about that. For example, by using the standard model, you can predict what the neutral current electric form factor should be as a linear combination of the up, down, and strange form factors. Okay? So these were the experiments. The first one was sample at MIT Bates. We just had an open air Cherenkov detectors to do elastic scattering at backward angles. And then you had the Mainz experiment in Germany that used a fast counting. This was the first experiment that tried to do parity experiment by counting individual particles. Okay, so these guys invented a very complicated electronic method to do this counting, and dealt with all the dead time, et cetera. And the rates were of the order of megahertz, and they did a pretty fantastic job of doing it. But that cannot be used anymore for the higher rates we've got now. Then there's HAPEX at Jefferson Lab, which is what I'm going to talk about in the next slides in Hall A. And then there was also the Hall C experiment, G0. I won't talk about it at all, which was a superconducting spectrometer which simultaneously measured a whole range of different Q squareds. Pretty interesting experiment that was done in the 90s. The asymmetries were typically tens of parts per million, so those previous generation experiments were very important to set up the technology. So here is the HAPEX Hall-A proton parity experiment, HAPEX. So this is kind of showing you, I do this picture a long time ago, and then I realized I actually turned the beam the wrong way. I turned it to the left towards Hall C, and I called it Hall A, but this is just a cartoon. So here is the basic thing. The idea is that the entire accelerator is part of the experiment. It's very important that we treat this as the experiment as a whole. So HAPEX 1 ran 98, 99, HAPEX 2 ran 2004, 5, and also the helium-4 experiment was done. So here's the key issue, why the Hall-A spectrometers are fantastic for this kind of experiment. So at 4 GeV, 12.5 degree scattering angle, which is the smallest angle that you can take the HRSs, there is enough resolution that the elastics and the pion threshold, this is in meters, are separated. There is a gap. So I just have to put a detector that just intercepts the red and stays away from the blue. And then I can just integrate, right? And I don't have any inelastic scattering to worry about. So this is the why you have this incredibly amazing spectrometer. So you can have this clean separation. And that is shown here. This is a classic QQ DQ HRS. And then we were able to just integrate the scattered flux. So I'm just going to show you the HAPEX 2 result. This was the very first time that at Jefferson Lab, we controlled the polarized source at the level of tens of nanometers. This is in microns here. This is showing you the X angle BPM, and this was a big deal to get down to this level. This is the actual asymmetry plot, and you don't have double vision. There are actually double dots here. We are trying to show you that the raw and corrected asymmetries are basically superimposed. There's barely any correction at all, and that has to do with how good this was. Okay, so there's very little correction to be done. So this was the asymmetry of hydrogen, a 1 part per million with a 100 part per billion error. And then helium is a bigger asymmetry, opposite sign, because you have so many neutrons. And that was also a very precise measurement. And from that, you were able to get 2 different linear combinations of the electric and magnetic strange form factor. This was published in 2007. We were able to rule out strange models that were at that time. But now, so over the past 20 years, lattice QCD has been a big deal in predicting these strange form factors. So in fact, what have we learned since then, and what kind of theory has progressed? The main thing is, by taking all these experiments at 3 different Q-squareds, we were able to separate the electric and magnetic contribution. We're getting 0 everywhere. You can see you're always intercepting 0. So we don't see a non-zero strange form factor. So what have we learned? We've learned that strange quarks are no more than a few % of the proton's electromagnetic structure. And this has been very important for all kinds of other experiments at Jefferson Lab. We can just ignore the strange quark contribution. Okay, we would not have known that but for these experiments until lattice QCD came along. In the past 10 years, though, so 2015, predictions were made for what these numbers. This is the same data as here, and you can see that lattice QCD claims they're non-zero, but in fact, they are non-zero, but they are an order of magnitude smaller than our sensitivity there. Okay. People are still thinking about whether we can get down these error bars. It's not trivial to do. Okay, so that's strange quarks. All right, now we come to neutron skin of a heavy nucleus. So let me motivate that. So here is the standard. If I just elastically scatter off a heavy nucleus, here's the standard amplitude, 4 pi alpha over q squared times the charge form factor, right? So if I have a spin 0 nucleus, I just have 1 form factor. Spin 0 isospin 0, then I have only 1 form factor. That's what lead is. So you just have the charge form factor. So let's look at the density in the lead nucleus, what do we know about it? So let's focus on the dashed curve first. The dashed black curve, the red curve is the proton distribution. And that's shown here. And the reason we know it this well is because of all of the elastic scattering experiments, like the first plot I showed you in the beginning of the third lecture. So we know the shape really well, okay? And the solid curve is the mean field prediction for this using all of the data on nucleon-nucleon interactions, et cetera, how well it can reproduce this curve. The dashed black curve is the neutron distribution, right? Neutron is, in fact, expected to occupy a larger volume. In fact, if you look at the charge radius of lead-208, it's 5.5 femtometers. And unfortunately, we don't have enough information about neutron-neutron interactions to be able to predict this. So there is a big error bar on this dashed curve, okay, which is not shown here, because there are many models that make different predictions. So in fact, the neutron radius is anywhere from 5.6 to 5.9 meters. Now, what is the black curve? That's the weak charge, the weak distribution. The weak distribution almost mimics the neutron distribution. Why is that? And that has to do with this accident of the standard model. Obviously, electromagnetically, you're sensitive to protons and not neutrons. But if you do Z scattering, the neutron coupling to the Z is much, much larger than the neutron coupling to the proton because of this 1 minus 4 sine squared theta W factor. If I take U plus D, I get 1. If I take U plus D, I get 1 minus 4 sine squared theta W. Okay, so that accident makes the Z scattering much more sensitive. So here are the two terms, the neutron form factor and the proton form factor, and this is highly suppressed. So effectively, when you measure the asymmetry of lead, you are measuring, you can almost ignore this point, which was the point of Q weak, was measuring this. But then in Q weak, this factor was extremely tiny. That's why you do it off the proton. But here, you're just measuring this piece, which is all the neutrons, right? So therefore, you're effectively measuring a constraint on this distribution, the black distribution here, which is what you want. You want to try and constrain this better. And it turns out that by making a precise parity violation experiment on lead-208 of elastic scattering, you can measure the neutron radius to 1%, which would be like 0.05 in these units, right? So that's what was proposed for lead-208 and also calcium-48, two doubly magic nuclei with lots of neutrons. And that was PREX and CREX. So for example, here are the mean field models, and they are spanning a big range of the difference between the neutron radius and the proton radius, which we call the neutron skin. And this is like the neutron skin going from 0.1 femtometers to 0.3 femtometers, that range 5.9, 5.6 to 5.9, right? And these are all the models, but you can see there is a linear correlation between the prediction and the asymmetry. And so if you measure the asymmetry, you can then measure the skin thickness to 0.07 femtometer. Now, why do you do two nuclei? It turns out that these mean field theory predictions can vary quite a bit for a neutron-rich light nucleus versus a neutron-rich heavy nucleus. And for example, they can't even decide whether the neutron skin of calcium-48 is heavier, is bigger or smaller than the neutron skin of lead-208, right? So this line is, they are equal. So this is the goal of the two experiments, PREX and CREX, to put a ellipse like this on this plot to choose between these models. So PREX ran in 2019, CREX ran in 2020, and that was exciting. There were lockdowns. We ran through lockdowns. Actually, it was kind of amazing. There were two people far from each other in the counting house. There were two people in the MCC far from each other in the counting house. Everybody else was at home. And that's essentially how we ran. There were only safety people in the lab. It was kind of amazing. So we started running in March. We were shut down. We were told to go home. And then 2 months later, we could come back in masked, and we finished the experiment. It's pretty amazing. Okay. So here is Prex and Crex. Here are the parameters for Prex. 4 gigahertz rate, very tiny Q squared, 600 parts per billion, asymmetry, 16 parts per billion goal to measure the neutron skin to this thickness. And then Prex, it is a higher Q squared, so the asymmetry is bigger, like a whopping 2 parts per million. The rate is much smaller than here, 100 parts per billion uncertainty, and it measures the skin to this thickness. So this is Hall A, of course. This is the right, pointing to the right hall here. Now, the lead 208 target was one exciting thing. Okay, here's a cartoon of what we do. Lead melts very quickly. You put an electron beam through lead, you punch a hole immediately. So the way we do this is we take a lead foil, we sandwich it between 2 diamond foils, basically carbon-12, right? Diamond. Why diamond? Because it's a good conductor of heat. And then these holes here, this jacket is copper, and these holes is where helium gas was flowing through at 20 Kelvin. So we're trying to suck the heat out before the lead died. Okay, so it was kind of an amazing thing. So here is what it actually looks like. Why do we have so many targets? Because we knew we were going to punch holes through them. Okay, so we just kind of moved target to target. Now, it turned out that by the time we ran this experiment, we knew enough about the technology not to punch a hole right through. But it turned out that after a few days, a week, the lead target became extremely, it had all kinds of weird bubbles in it and so on. And it became very uneven. And then you had a raster, and there were all kinds of problems doing the parity experiment. So we moved from target to target every week. In my backup slides, there's a picture of what the targets looked like after we finished the experiment. So that was one thing. So here is Crex, Prex. These are the final results. But because of the fact that Prex was the latest parity experiment done here at the lab, I'm going to now take some time to just walk you through how we do the analysis, okay? Because we're going to do the same thing for molar. Okay, so we have window multiplets. So this, for example, is 240 hertz rehearsal. You always want to be in some unit of 60 hertz. So, so we choose a random number, and then you go plus, minus, minus, plus, and then you choose a random number, and you either go minus, plus, plus, minus, or plus, and so on. Yeah, and then you choose a sequence like this. And then for Prex, we are trying to get to 10 part per billion. And the statistical width at 30 hertz is 100 parts per million. And that's what we were trying to show. And the main thing is that at this level, even the unevenness of the target plays a role. And you have to try and find ways to correct for all kinds of fluctuations, first order and even second order. So you must minimize both the random and helicity correlated fluctuations in this pair response in order to, so what is shown here is for example, when the beam flips sign, when the beam intensity changes when you flip the sign of the helicity, and that makes this jump around, and the detector is jumping around, so you need to correct for that. So you need to know what to do by measuring the intensity well enough so that you can correct for this fluctuation. Likewise, the energy of the beam is jumping around, and you need to correct for that. Notice this sign changes because cross-section goes like 1/e to the power something. So this is a positive correlation, this is a negative correlation. So you got to look at all these correlations. After correcting, then you want to make sure that you only have counting statistics left. And the goal was that the corrections are no bigger than the statistical uncertainty. So over minutes, you got to make corrections at the level of parts per million, microns in the position. Over days, it's parts per billion, and then nanometers over the position and so on. You have to average it continuously. So here's an example. I won't go through this plot in detail of this is what we saw when you just look at the raw detector asymmetry, and after all the corrections, this is what you end up with. This is critical that you do this correction because if you are stuck with this, you can still do the experiment, but it'll take you 4 times longer, right? Because the width is, 10 times longer, right? The width is 3 times bigger almost, right? If the width is 3 times bigger, it'll take you 10 times longer to do the experiment. So it's critical that you do this right. And so then you have to look at the statistical properties. So this is a whole bunch of 5-minute samples. And you can see that it's non-zero, the average. That's your asymmetry, 500 parts per billion. What I want to focus on is this plot. This red line is not a fit. It is a Gaussian of unit variance. You just put a Gaussian with a variance of 1. That's what this is. So all I'm doing is for each of these 5-minute runs, I'm plotting AI minus A bar over sigma I. The asymmetry minus the average divided by the error. And I just put it on this plot. No fit. It sits right on a Gaussian of unit variance. That is a big deal. It shows that we understand our statistics. Okay, so there is even in the 5,000 points here, there is even like a nearly 3.5 sigma point right there. I remember being in the hall when we measured this, and everyone was freaking out, and I said, just keep it. Let's see where we are after we do everything. Right, so here we are. It's kind of amazing. Statistics at work. Okay, so this is now 6-hour time scales. You want to look at all different time scales. Throughout all of this, everything is blinded. There is an arbitrary offset on everything, a small one. It was plus minus 100 parts per billion or so. So you can study everything and still not know the real answer. This is a powerful plot. This is all the data, 33 millisecond flips. All the data. It is a perfect, this is not Monte Carlo, this is data. This is a perfect Gaussian over 5 orders of magnitude. You can't produce a plot like this without a parity experiment. 5 orders of magnitude Gaussian, perfect Gaussian. Okay? The small tails here are completely irrelevant because it won't change the central value. So this is actually the minus 500 parts per billion is sitting there. This is in parts per million, so you can't see it. That's the average sitting there. Okay, but the fact that this is a Gaussian over 5 orders of magnitude is a big deal. The corrections were only about 60 parts per billion, so that's the triumph of the machine and the control from the polarized source. That's what we have to try and do. Okay, so again, we do the kind of tests by looking at half-wave plate, and then there were another way to flip the sign of the asymmetry. Here are all the systematics. You can see the total statistics are 16 parts per billion, systematics 8 parts per billion. And then finally you get this, and at this point, you're ready to unblind. This is a big deal in a parity experiment. You get everybody together, and we start writing the paper, and you're ready to unblind. It's actually a very exciting event. It kind of, when you sit through that and your pulse starts racing, you say, okay, this was all worth it. It's very exciting to do that. When we did this, the answer came out to be the same. It was bizarre because we had a flat blinding blocks of plus minus 160 parts per billion, and we ended up having a offset of nearly 0. So in fact, we were very freaked out about this. So the way the blinding is done is that one graduate student picks a text string, and the text string is then stuck in, and then it generates a random number. And our text string was, roadkills 2 sounds mighty good right now with these things. And we wanted to, and if we had tried to change something in the text, you'll get completely different answers. We had to go double check that we had it right. Why was this chosen by the grad student? It turned out he was on shift and he heard two security guards talking, and one of them made this statement. Anyway, so this is kind of the crew for PREX. So grad students, spokespeople, run coordinators. So this was a big deal. This was finished in 2020. Okay, what did we get from PREX and CREX? So this is the PREX result. And the main thing for the theorists is this form factor, weak form factor at this Q squared. The rest is interpretation. One way to interpret the result is to use this form factor and then come up with a neutron distribution by using a model for the overall shape of the lead nucleus, which is a fantastically spherical nucleus because it is spin zero, isospin zero, doubly magic, right? So that's what this is, and the blue, light blue is the error bar. But what is a really cool thing that nuclear theorists pointed out to us is by taking this, which is well known, the charge radius, charge distribution, then you sum it and you got the interior baryon density, and you get this number, 0.148 plus or minus 0.0036. Now, this number 0.15 is something you might have seen in nuclear courses or textbooks. This is the interior baryon density of nuclei. This is the so-called, this is the 0.15 number, right? So this is a direct measurement of that. It's kind of a cool thing. You don't know how to do that otherwise. Okay, you infer it, you use nuclear theory, right? But this is a direct measurement because you made this measurement, and then you already knew this. So you add the two, that's it. See, calcium-48 is here. Here, again, the form factor is what the theorists care about. And then I can put the two together. The charge minus the weak form factor, charge minus the weak form factor for lead-208, calcium-48. Now, notice this is zero suppressed. The fact that these are far away from zero tells you unambiguously that the neutrons bulge out above the protons in these two nuclei. It is a direct measurement of it. It's an electroweak measurement, very clear, not much theory involved. The fact that these are away from zero tells you that neutron radius is bigger than the proton radius. But of course, they care about where you sit in this curve, and here are the theories. And we are right at the edge. We almost killed the theories. They did not make the nuclear theorists very happy. We killed some theories. This is the diffractive optical model. And this set of gray lines is what the theorists believe. And what they're changing here is the symmetry energy of dense nuclear matter as they move it around, and we seem to be close to here, which is actually where everybody wants it to be. But the fact that we nearly are in disagreement is a little uncomfortable. So the PREX measurement has very little model uncertainty. The CREX measurement is challenging to improve. The community lore is that this should be here and that should be over there, which means that the calcium-48 skin is too thin and the lead skin is too thick. But I am actually suspicious that they don't know what they're talking about. And that that they're missing some dynamics. Now, how do we test this? Why do we care in the first place? The idea of the neutron skin has implications for nuclear structure physics, but it also has implications for neutron star physics, atomic parity violation, coherent neutrino scattering. So let me start with this Google picture of the semi-empirical mass formula. You have a volume term, a surface term, a Coulomb term, and the asymmetry term. The asymmetry term is the Pauli principle, right? That you can't have fermions in the same place. And that goes by that is proportional to not the asymmetry term, but the symmetry energy of dense nuclear matter. So the symmetry energy of dense nuclear matter has this symmetry energy term where if you define delta to be the neutron density minus proton density over the average density, and then as you increase the neutron density, how does this symmetry energy evolve? The density dependence of the symmetry energy is a big deal in nuclear theory because for two reasons. One is the density dependence of symmetry energy is directly correlated to the size of the neutron skin. The larger the slope, the more the neutrons tend to bulge out. So you want to measure this slope. And another reason is that this is the slope you need to predict neutron star density. Now, I want to make sure all of you had take the small change in scale between here and here, between these two circles, okay? To make sure you've processed that. But in fact, the interior of these two have the same kind of nuclear matter, okay? So this now relates to LIGO, for example. What is this picture here? This is the famous LIGO Livingston chirp for the neutron star binary merger. And this picture is a simulation of how the neutron stars become pearl-shaped just before they collapse on each other. Just imagine that you have neutron nucleus the size of Manhattan, and it is going to bulge out because of the proximity to the other Manhattan-sized object near it. And this amount of bulging depends on the symmetry energy. Okay, so there's a parameter that LIGO can measure when they see the ring down of the neutron star before it makes a black hole. So the neutron star radius, this is called the binary inspiral tidal deformability. Okay, because it's tidal forces, right? Now, there's another way that you can measure the neutron star radius, which is kind of very cool. You take a pulsar and it's rotating, and you measure its oscillation as it rotates. But here's the deal. General relativity makes it so that when the pulsar is pointing away from you, the light bends and comes to you anyway. That's kind of wild. So depending on the neutron star radius, how much of that light comes to you is changed. So by looking at those oscillations and doing a general relativity calculation, you can actually predict the neutron star radius. So that is this satellite experiment called NICER. So you get the neutron star radius from three completely different things. And my hope over the next decade is that these measurements, they will see some more, I hope, will lean towards what PREX measured. And so the nuclear theorists will be forced to actually go review what they're seeing. It'll be interesting. Now, in order to force this issue, the question is, can you do better than PREX and CREX? And it turns out that there is an experiment called MREX at Mesa, which will try to measure a factor of 2 better than PREX. And if they measure something that is at our edge of our sigma, then everything is good. But if they measure it here, that will create trouble. And that's what I'm rooting for, if they do that. So this is very compelling to try and reduce this by a factor 2. And we are hoping that that will run in the early 30s. Okay, so how much time do I have?
20 minutes.
Yeah, okay. So I'm now shifting gears now to the electron-ion collider. Okay, so I don't know how much people have talked to you about the electron-ion collider in your lectures. I looked through it and I couldn't tell. So you haven't talked about it at all. So I stole this picture from a friend of mine. I wasn't really planning to talk about the electron-ion collider, but you should know that you're going to have polarized electrons, polarized and polarized protons. The fact that you have double polarization is a big deal with very high luminosity. And here are the proton energies, the electron energies. So this is the EIC. So just think about the fact that we hope 10 years from now we have this collider in operation. Okay. All right, so this I think you kind of know. I just put down deep inelastic scattering, the various parameters, and where EIC is going to come. So I'm not going to talk about this either. Okay? Here is where I'm going to slow down a bit. Now I'm going to talk about structure functions. You probably already know your electromagnetic structure functions, F1 and F2. But now I am going to have structure functions that also involve W and Z exchange. Okay, so instead of just having F2 gamma, I now have, again, remember the vector and axial vector couplings times F2 gamma Z. This is the interference structure function for electromagnetic weak interference. So you have new structure functions. And then you have the pure Z exchange structure function, F2Z. You also have the F3 terms now. Why you don't have an F3 gamma? Because F3 is parity violating. So you have an F3 gamma Z and F3 Z, and then you have F1W, F2W, and F3W. All of these structure functions. Here's a summary of it. So again, you need the Weinberg model, neutral current cross-section, pure photon exchange, weak electromagnetic interference, pure Z exchange. You got to do it all together. You have these triad of structure functions now instead of just a simple one. And then you have the charge current structure functions for W exchange as well. All of this will be measurable at the EIC because of the high central mass energy. Okay? So here, let me slow down a bit. Why are these new structure functions interesting compared to the ones you're already used to? So first of all, let me produce an asymmetry. So this is a big deal at the EIC, is that your polarized electron and the proton are longitudinally polarized pulse by pulse. Pulse by pulse, you can flip the sign of either polarization. So you can make left, left, right, 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 left, right, all four combinations. Okay? Now, the big deal about one of the first things that EIC will do is look at the double spin asymmetry and measure the G1 structure function, which is a purely electromagnetic spin structure function, which will allow you to get deep insight into the spin of the proton. Okay, so that will come much faster, the EIC. But if I now take average over the proton polarization and just look at the left-right asymmetry with where the electron polarization is flipped, but you average over the proton polarization, that's a parity violating asymmetry. And that Z exchange, gamma Z interference, right? So that's just like what we did at fixed target. And that's what this asymmetry is. When the electron is polarized and I average over the hadron polarization, I call that the APV. And then the other way, where I average over the electron polarization and I just flip the hadron polarization, I call ATPV, unpolarized electron, polarized hadron. And they give you access to new structure functions. F1 gamma Z, F3 gamma Z, G5 gamma Z, G1 gamma Z. Why are they interesting? F1 gamma Z is proportional to U plus D plus S PDFs in the quark parton model. Those of you who remember what F1 gamma looks like, does anyone remember? It's U plus 1/4 D plus 1/4 S. Why is the 1/4? Because this charge of the D quark and the S quark is half the charge of the U quark, right? The electromagnetic charge. But the weak charges of U, D, and S are approximately the same. Therefore, you get U plus D plus S instead of U plus 1/4 D plus 1/4 S. So you've got a different linear combination of PDFs compared to ordinary F1 gamma. The other big deal is G1 gamma Z. You get delta U plus delta D plus delta S, as opposed to delta U plus 1/4 delta D plus 1/4 delta S in the G1 gamma case. Okay, so again, that's why this is so useful. And so you can make these measurements. The electron asymmetries then, once you measure this, is also sensitive to the weak mixing angle. So you can make new weak mixing angle measurements. You can also use deuterium instead of the proton, and then their nuclear physics effects cancel out, and you can measure the weak mixing angle without much PDF uncertainty. Okay, if you want to use the proton, you must know the PDFs very well, so you will simultaneously do PDF fitting. This is ongoing studies. So you need studies are required both at low Q squared and high Q squared. And then there's a lot of theory work that needs to go in to get the radiative corrections right that hasn't happened yet. Okay, so all of this is ongoing work. The hadron asymmetries access to an entirely new set of structure functions, as I said, and will contribute to flavor separation of the polarized PDFs. Okay, that's going to be a major contribution from these. So a few of us did a study some time ago. EIC has been around as an idea for a long time. This was published in 2017, showing you the asymmetries that you will measure as a function of X. So for this case, there is a paper out there. And then how well do you measure the structure functions? Now, this is the error bar, relative error is 100%, 10%, 1%. So it's only these that are interesting. So let's zoom in over there. So these numbers will be extremely interesting. So you can see the X at which it's interesting is of the order of 0.1. Okay, so over here, we're going to make some very interesting measurements. It depends on the center of mass energy, luminosity, et cetera. So these are not day one measurements. You need lots of data. If you use the deuteron, you can make weak mixing angle measurements with very little PDF uncertainty, and this was a prediction for how well we will do. It's a very different place than where everything else is, right? So that's kind of interesting. You also have, why do we want to do all of this? What is the landscape in 2035 as LHC discovered new physics? Presumably, these measurements have been done. Now, I don't know about SOLID yet, whether it will still be running or hopefully at least has been funded by then. But we're hoping these kind of measurements are done by then. So there are models out there that say that this running will change if I have a dark Z. There are papers. There's also the idea of measuring the weak mixing angle in a very new kinematic regime. The measurements help constrain UDS PDFs. If they're well known, then we can make these measurements much more precisely. In fact, a study was done where they assumed that the PDFs will be much better known from the EIC itself. And they used proton data, and they were able to come up with better numbers. And then they worked with theorists to do the standard model effective field theory analysis for looking for new physics at the EIC. And I won't go through this, but they were able to show that there were regions of parameter space in these new 4 Fermi. So these coefficients C here are what is listed here. That there are regions of parameter space where they are complementary to LHC. So a lot of this is coming from LHC Drell-Yan. There is no polarization at the LHC. So because you have polarization at the LHC, you get slightly different linear combinations. And so, for example, here is an example where this is LHC right here, and EIC can make a contribution, for some specific combinations of these new 6-dimensional operators. Okay, so EIC is going to be useful for this. So this is a more recent study looking at this kind of new physics analysis. Again, the hadron asymmetries, the TPV, ATPV, G5 structure functions. So this is the study of how well we can measure them at the EIC. And again, 100%, factor 10, 10%. This is going to be a hard measurement. So if you zoom in there, right here at this X, high X, you can measure it to maybe 10%. This will be an important input for the strange quark polarization contribution. Okay, because otherwise, the only way to get a delta S is to use semi-inclusive measurement, which comes with its own can of worms of theoretical uncertainties. So the next steps, this is actually ongoing work. We are working on trying to do better. We have to see how we do global fitting to try and improve this. How well are we going to do this? This is actually current work going on. Okay, so that's it. So that's kind of my broad brush view of how parity violation might be used at the EIC. And so this is the final slide. Okay, so today's lectures were kind of, as I said, an independent look at parity violating electron scattering. And this is the takeaway message from that. And yesterday's lectures were more lectures. Today's lecture was more a 2-hour colloquium. So today, we've learned that parity violating electron scattering has enabled unique studies of the weak force, technical progress has enabled unprecedented precision, fundamental nucleon physics, strange quark, form factors, neutron RMS radius, valence quark structure of protons and neutrons, new structure functions, and then fundamental electroweak physics, search for new dynamics at the TeV scale, complementarity colliders, precision measurement of the weak mixing angle, and then we are hoping that the first physics results from Moeller will start flowing by late next year. Okay, I'm ready to conclude.
Are there any questions now?
Yep.
Yeah, I just had a question. With the EIC, what is going to be the flip rate for polarization?
So I think they have a stream. Their pulse structure is tens of nanoseconds. So pulse by pulse, they can do this because they have these Siberian snake magnets. And then the polarized source can, of course, flip fast. So I think it's going to be just pulse by pulse, and they are very fast. It's much faster than what we do here.
Okay.
I had a question with the F1 like gamma Z structure functions. Are those like interferences between the electromagnetic and the weak force, or like you were talking about?
Yes. So they come directly. So if you wrote down I don't have the slide here, but you start off this way. You start off here, and then you write the most general form of the structure functions that you can for the cross section, assuming CP conservation, but you allow parity conservation. And then you get a whole bunch of structure functions is the most general form. And so once you do that, then there are this is multiplied 3 times. The alpha squared is for the gamma exchange, but then you get the alpha, then you have the interference piece, and then you have the pure exchange piece. Okay, so you have, and that's what is written over here, right? So these eta gamma z and the eta z are the kinematic factors that come in when you do interference. So this piece is the interference, and this is pure z exchange. And you can see that also from the fact that you have one factor of vector electron, one factor here, and you have the square here, because here the vertex is a Z coupling on both sides of the Feynman diagram. And here it is one side, it's the interference term, right? So yeah, so you have, this is the piece that I was focused on, because this piece is very small compared to this piece, because this is interference, and this is pure Z exchange.
So I guess a follow-up question with that is how, I guess, how does that unravel to tell you about the weak charge? Is it based on like knowledge of the like magnetic charge that gives you the weak charge, or?
Yeah, so essentially you write the asymmetry in this form, and you pick a xq squared, and when you have an xq squared, this kinematic factor will get determined. So you make at different xq squared values, you measure the asymmetry, and you will get a linear combination of F1 and F3, F1 orga. So you linear combination of this ratio plus this ratio. This ratio you know because you have done purely electromagnetic scattering. So you get a whole bunch of points, measurements of this plus this with a factor in between that depends on the kinematics. And then you're able to then separate them out by looking at different kinematic ranges. For example, if I just vary y, then I will get, and if I look at the y dependence of this combination, I'll get a line. The slope of the line gets you one structure function, the y-intercept gets you the other structure function.
Thank you.
Thank you for the talk. I had so actually about this slide, do you expect to see any like tensor spin observables when using polarized deuterium in the?
I think the observable, when you just do flip the longitudinal polarization, you're not sensitive to that. You would have to come up with a different kind of observable.
All right, thank
I
you.
haven't thought about it, but probably is possible if you use a different kind of observable.
Yeah, 'cause
If you're just looking at purely inclusive longitudinal flip, then you won't have sensitivity there.
okay, thank you.
It is possible to construct an observable, I imagine. I have not thought about it.
No, I was just thinking because like part of our group's work is we look for B1
Yes, yes, yes.
function, but
Yes, yes. So for example, if you have transverse spin, for example, which AIC is planning to do, there might be ways to disentangle.
all right, thank you.
Any more questions?
Okay, then let's thank Krishna again.